All right, welcome back, everyone. I've got a few announcements, and we're going to start with 2 iClickers. So I'm going to start down here. Our midterm is next class, so this Wednesday I posted an announcement about that, and it is all multiple choice. There's 24 questions. Currently, I think I'll keep it at 24. It's cumulative, so it has content from chapters 11, 12, 13, and 14. More so on 13 and 14, but there is a good chunk from 11 and 12. Make sure you bring a calculator and a pencil, and I'll provide everything else that you need. So the periodic table sheet, Scantron, scrap paper, I'll provide all of that. So keep that in mind for Wednesday. There is an Achieve homework due next Monday. That is short. It's just the end of chapter 14. So I think there's 9 or 10 questions. It shouldn't take too long, but keep that in mind. That will be due Monday. We'll finish 14 on Friday. And then there are also adaptive quizzes for chapters 11 to 14 available on Achieve. These are not due until a week from today, but they are a good study resource for the midterm. So I encourage you all to at least start working on them, and then these are for extra credit. So if you do complete them by Monday, 9 a.m., then each one is worth 1 assessment point. Will be added to the midterm or unit exam 1. My office hour tomorrow is 2 to 3 p.m., and my office hour Thursday is 2 to 3 p.m. Questions on any of this? Okay, we're going to start with 2 iClickers reviewing stuff from Wednesday, or from Friday, right? Yeah, Friday. So here we have an integrated rate law. If you check, one thing you should do actually, check if this is for a first order or second order reaction. In the equation, they've provided the value for K. They've provided the initial concentration of reactant A. And the question is, what is the concentration after 10 seconds? So you're calculating concentration of A at time t. And then the second question you all have is for this integrated rate law. You should also check if this is for first order or second order reactions. What plot would produce a straight line? Each of these, so we're thinking of a y-axis and an x-axis. This is y and x, y, x, y, x, y, x. So we're listing the y variable first. All right, I'll give you all some time to work on these 2, and we'll go through them. Where the natural law of destruction.
Oh, it's literally stated in one whole question. Bro, what's up? We were talking about this guy is weird, bro. Bro, let's get those chickens. Oh, yeah. Yes. Presence of agents of these data. Yes.
Okay, one more minute. Okay, closing it here. Okay, so first equation here, we have the rate law for a second order reaction. You didn't need to know that for this question, but that's just practice for when you see this on Wednesday. So we're given values for K in the initial concentration and time, and so this question we're just plugging in information. So 1 over A at time t, that's what we're calculating, is equal to rate constant 0.20 per molar per second times time. They told us that's 10 seconds plus 1 over the initial concentration, which they provided as 0.5. Simplifying the right side, we still have 1 over concentration of A at time t on the left. 0.2 times 10 is 2. 1 over 0.5 is 2. So we have 1 over concentration of A is equal to 4. Now we need to manipulate this to have concentration of A at time t in the numerator. So you could multiply both sides by concentration of A at time t and move it to the right, and then divide both sides by 4, and you'll have concentration of A at time t is equal to 0.25, 1/4. So that's D. Questions here? Okay, the next question, we're looking at the equation for a first order reaction, this integrated rate law equation. And the question is, which plot would produce a straight line for this reaction? The integrated rate law here is written in y equals mx plus b, or natural log of a. At time t, the concentration of a at time t is dependent on time. So that makes time our x variable and the natural log of a, of the concentration of a, the y variable. So concentration of, or sorry, for the natural log of the concentration of a plotted versus time t provides a straight line. The slope of the line is negative k. And then natural log of concentration of a at time 0 is b. That's a constant that's not going to change. So for a first order reaction, concentration of time, oh my gosh, concentration of a at time t, plotting the natural log of that concentration gives you a straight line. That does not give you a straight line for a 0 order or a second order reaction, only for first order. If this were a second order reaction, then you'd need to plot 1 over concentration of a at time t versus t. So t is still the x variable, and the 1 over concentration of a is y. And that would produce a straight line for a second order reaction. For a first order reaction, natural log of a versus time. Okay. Questions on either of these? All right. Moving on to, well, review what we talked about for collision theory and then some new content. So remember that reactions will occur only when reactants have sufficient energy, and that sufficient energy is what we call the activation energy. Reactants need to have enough energy to overcome the activation barrier, we call that amount of energy activation energy, in order to form the products. So they will collide when they have sufficient energy and when they are in the correct orientation. So for this reaction, we start with 2 NO molecules and we form N2 and O2. The 2 nitrogens have to be near each other, 2 oxygens have to be near each other for this reaction to occur. Here, the nitrogen and oxygens are lined up, so no reaction occurs because of that orientation. But remember, molecules are constantly moving around. So as long as they're in the correct orientation and have sufficient energy, that reaction will occur. So we can put an equation to describe that relationship, and that is the Arrhenius equation. We're going to talk about 3 versions of this equation. The first one was developed in the 1800s. I'll define all of these letters here. This one is a little bit easier to work with, and then the 2.1, which we'll discuss in a couple of slides, is most frequently used. That one is provided on your equation sheet. But first, let's talk about what these all mean. So K is the rate constant. Capital A is a frequency factor. And this is related to the frequency of collisions. Now that's really difficult to measure, and that's what makes both of these not as useful. But that's a frequency factor that would be unique to different reactions. E, capital E, lowercase a, this is activation energy. R is gas constant. in joules per mole times Kelvin because we are also working with energy values here, activation energy. So we'll use the joule version of the gas constant. And then T is temperature in Kelvin. So this equation demonstrates that the rate of the reaction, so K, the rate constant, is dependent on the frequency of collisions, that frequency factor, the temperature, and the activation energy. But like I said, that frequency factor is difficult to measure. And this equation in general is difficult to use. Also, another thing I'll say, that E, the lowercase e there, that's that function in your calculator. So you just plug in E and raise it to the power of negative activation energy over gas constant times temperature. The equation on the right is derived from the one on the left. That's where you take the natural log of either side and rearrange. So we've got natural log of K on the left. Now remember, if you take the natural log of E, the natural log and the E cancel out, we just get that exponent. So that is that fraction there times 1 over temperature, and the natural log of A would be a constant. So this is now in a y equals mx plus b version. Where x is temperature. As you change temperature, rate constant will change. Okay, so why is this easier to work with? Well, if you have temperature of different reactions and can measure the rate at those temperatures, then you could plot a line where you have temperature on the x-axis, or 1 over temperature on the x-axis, natural log of the rate on the y-axis. Find the slope of that line, that will be activation energy over R, and the y-intercept will be the natural log of A. So experimentally, this one is easier to work with than that one. That requires more steps. But well, let's do that for this equation here. We're going to be provided on the next slide some values for a reaction, and we will calculate the activation energy. Now, I did some of the steps for you. Well, the book did some of the steps for you. So let's say we're working with this reaction. We have N2O forming nitrogen gas and oxygen gas. And this reaction was run at 4 different temperatures. And at those temperatures, the rates of the reaction was determined, or the rate constant was determined. So we have temperature and rate constant for the 4 different temperatures. So we can use this equation. Natural log of K equals negative activation energy over R times 1 over T plus natural log of A. That's that y-intercept. So plotting rate constant versus temperature provides a straight, or natural log of rate constant versus 1 over temperature provides a straight line. And the slope of that line is activation energy over R. So if you were just given the values, you'd have to plot those points and find the slope. That's what was already done for us. So slope, which is negative activation energy over R, is equal to negative 30317. And our goal is to calculate activation energy so we can simplify and solve. Now the units for slope here, knowing that it's activation energy over R, that's joules per mole over joules per mole times Kelvin. So the slope units is just Kelvin. And we'll end up with joules per mole for the activation energy. So activation energy, now multiplying both sides by R. Both sides of the equation are negative, so we will remove the negative. Multiplying these two values together, we have 252,000 joules per mole for our activation energy. Or 252 kilojoules per mole. So remember, rate constant depends on temperature. For a reaction to occur, the reactants must have sufficient energy. They must have the activation energy for that reaction. When more molecules have enough energy to overcome that barrier, the rate will increase, rate constant will increase. So we can see an increased rate constant based on increased temperature. And when we're comparing how much that temperature increases versus how much that K value increases, we can determine then what energy is required for the reaction to occur. And that's what the Arrhenius equation in general is relating for us. The next slide has the 2-point version. This is the version that's on your equation sheet. And this version allows us to avoid the graphing. So as long as you have two values of temperature and rate constant, then you can plug those directly into this equation. You don't have to plot anything. So this one provided on your equation sheet. And this is useful for determining activation energy when you know the rate and temperature at, or when you know the rate constant at two temperatures, or any of those variables in the equation. So now let's use the same data that were provided on the previous, or 2 slides back. And now instead of plotting, finding the slope, going through that equation, use the 2-point equation and find the activation energy. You could use any 2 sets of data. Just to keep it consistent for class, let's use the first 2 rows. But any of the rows should give you approximately the same activation energy. So we're using that 2-point equation, natural log of the rate constant for one reaction at one temperature divided by the rate constant for at another temperature is equal to activation energy over R times 1 over T2 minus 1 over T1. I'll give you all a minute or 2 to get started on this.
New York, P2. Oh, I don't want that. It should be the same, almost the same. I believe you. You know, yesterday I played with the AI, right? Just for fun, but no, the thing is, look, I was studying chemistry, right?
All right, let's put in these values and calculate the activation energy here. At this point, we are simply plugging in values and simplifying the equation. So using the first row as experiment 1, second row as experiment 2, or temperature 1, temperature 2, and rate 1, rate 2, we'll have the natural log of rate for T1, which is 0.0018 per molar per second, divided by that second rate, 0.175. Now look at these values here. As we're increasing in temperature, we're increasing in that rate constant. Increasing temperature will increase the rate. So this is equal to activation energy, which is what we're looking for, divided by gas constant, 8.314 joules per mole Kelvin. 1 over T2, 975 Kelvin, minus 1 over T1, 850 Kelvin. Simplifying the left side, the natural log of that fraction, negative 4.5769. Now, what I did next is simplify what's in parentheses, 1 divided by 975 minus 1 over 850, and then divided by 8.314. That gives me a value that should be multiplied by activation energy, 0.0000, so 4 zeros, 1814. Mole per joule times activation energy. Are there questions about what I did there? Yeah. Like, take the natural log first, get this, and then multiply by that. Or divide. Yeah, well, you would multiply because it's getting divided over here. So
I subtracted the one for 975, one for 850.
You got a value?
Yeah, I got one of them. And now,
Okay.
oh, wait. No.
Okay. There's certainly different ways to go through that step. I just simplified everything on the right first and everything on the left first, and then now we'll divide both sides by that really small number. And that provides 200, oh, that should be negative. Sorry about that. 252,302 joules per mole is equal to activation energy. Or if we convert that to 3 sig figs in kilojoules, 252 kilojoules per mole. So same value as what we did 2 slides back by plotting all 4 data sets, finding the slope of the line, and calculating activation energy, or with just 2 data points, then you can use this equation to calculate activation energy. And again, we're thinking about or calculating really the relationship between temperature, rate constant, activation energy. Reactions have a certain activation energy. If you provide more energy to reactants by increasing temperature, they will get to that activation energy. More molecules will get to that activation energy quicker. That increases the rate. So by knowing how rate constant is affected by temperature, we can then calculate what that energy is. And that's what we're doing here. Yeah. No, but I tend to, if the value is really large, like if joules is really large, then I'll convert to kilojoules. Or if I calculate kilojoules and it's really small, I'll convert to joules. For like achieve for our assessments, it will either not matter or it will say like calculate kilojoules or calculate joules. Other questions? Okay, let's go to 14.5. So this is about reaction mechanisms. We'll define what a reaction mechanism is and elementary steps, which are reactions within a reaction mechanisms. We'll talk about a bunch of different properties for these. So something like photosynthesis. This is a chemical reaction that occurs in many steps. Photosynthesis can be summarized by that equation at the top there. Carbon dioxide and water forms carbohydrate and oxygen. That's an overall reaction mechanism is what we will call it this semester for photosynthesis. But the actual reaction of photosynthesis is many smaller elementary steps. So I've got this image here to show photosynthesis. The Calvin cycle also has a bunch of different steps. Anytime a bond is broken or formed, that's a chemical reaction. So right here, this little part here, converting from ATP to ADP, that's one step, one elementary step in the entire Calvin cycle. And then you zoom out even further and you've got photosynthesis. So we've been talking about reaction mechanisms as independent of their elementary steps, but now we'll kind of go into those puzzle pieces, so those elementary steps that make up the full reaction mechanism. Not for something this complicated though. That's not till biochem. Okay, so just to reiterate, reactions can occur in one step. That is possible for one reaction to have one step, but many reactions occur through multiple elementary steps. So that means there are multiple molecular events or times where a bond is breaking and or a bond is forming. So these multi-step reactions can be described as a series of elementary steps. Next slide is all about elementary steps. So each elementary step like that one section of the Calvin cycle where ATP is converted to ADP or vice versa, I don't remember. Each step has its own activation energy, so that it has its own set of reactants and products, has its own activation energy, and will form its own transition state. And then after that transition state, if it's not the very last elementary step, it will form what we call an intermediate. That intermediate then continues to react in the next reaction. So elementary steps have their own activation energy. Excuse me. Thank you. They have their own activation energy and their own transition state. Let's look at this very general reaction. We're not even using real molecular symbols. We're going to say the overall reaction here. We're starting with reagents AB, so A is bonded to B, and we're adding C. They will react to form A bonded to C and B on its own. So in this reaction, we break the A to B bond and we form an A to C bond. In this made-up reaction, I'm also going to tell you that it occurs through two elementary steps. The first step, so with its own activation energy, with its own transition state, the reagent AB is broken, that bond is broken, now we have A and B. So we have a decomposition reaction first. Then in the second step, another activation energy, another transition state. A, which was formed in step 1, reacts now with C, the last reagent, to form AC. So again, this is a general example of an overall reaction that occurs through two elementary steps. It's not always the case that the first step a bond is broken, the second step a bond is formed. This is just an example of where two steps create the overall reaction. So when this reaction is occurring, when we have elementary steps, a portion of the reactant molecules reacts to form a short-lived unstable intermediate. Looking at this example here, step 1, we have a portion of the reactant, meaning AB, that reactant is reacting to form A and B. B is a final product, but A is not a final product. That is the unstable, short-lived intermediate that then reacts with C. So the intermediate reacts with remaining reactant C to produce the final product, AC. So on a reaction coordinate diagram, we got step 1 and we have step 2. Step 1, reactants are AB. We'll say they're at that energy level. AB, they've got activation energy, transition state, and will form A and B, but A is that intermediate. So this intermediate, I'm abbreviating as I, is that reactant A. Higher energy than the reactants. It's unstable, meaning it's higher energy. Short-lived, because it's going to react as soon as it's formed with that last reagent, C. So then we've got another transition state, another reaction step. Transition state 2, and then finally B and then AC are formed as the products. So however many elementary steps you have, that's how many transition states are there. Each transition state represents one step. We've got activation energy from here to here, activation energy from there to there. So 2 activation energies, 2 transition states. In between transition states is where the intermediates are.
So like, wouldn't step 2 drop the energy though because you're forming the bond? Why does it still go up for both, like breaking the bond and forming the bond?
Because we still, yeah, that's a really good question, but you still need enough energy for the molecules to collide. Any reaction, even if it is forming bonds, so a composition reaction has an activation energy. For this reaction, I'd put the 2 transition states at similar energy, but the second one in reality, since we're just forming bonds, would probably be lower. But that's not something that you all need to know at this point. Okay, so we've got our 2 elementary steps, the overall reaction mechanism. We can use those elementary steps to understand the rate of the overall reaction, but we need to know the relationship between them. So that overall reaction, we are calling the reaction mechanism. The reaction mechanism is the sum of all elementary steps for a reaction. That's what we saw on the last slide. A, B formed A plus B, and then A got used up, reacted with C, and formed AC. This is a real reaction here. So this is nitrogen dioxide reacting with carbon monoxide. This occurs with 2 steps. The first step, 2 moles or 2 molecules of NO2 react together to form NO and NO3. That's the first step of this reaction without even using that second reactant. So that has to occur first. Let's put words to what those reactions are. I'm going to do that up here. So 1, 2 NO2 molecules collide to form nitrogen monoxide and nitrogen trioxide. Those are the 2 products after that first elementary step. In the second step, notice that reagent is NO3. That was generated in the first step and then is used in the second step. That reacts with carbon monoxide to reform NO2, the original reagent, and form carbon dioxide. So NO3 and CO, carbon monoxide, collide to form CO2 and reform NO2. Said reform because that was a reagent. The overall equation here is the sum of both of these, but do y'all remember when we wrote out ionic equations, ions on the left side sometimes repeated on the right side, and we'd cancel them out if they were present as a reactant and a product? That's what we'll do here, but for basically adding these 2 reactions together. So we'll go first, we'll talk about all the reactants, and then we'll talk about all the products. Overall equation is the sum of these 2. For the first reactant is NO2. We have 2 moles of NO2 on the left side and 1 mole of NO2 on the right side. So this cancels out with 1 mole on the left. So in the overall equation, the reactant is 1 mole of NO2. So we leave the coefficient out. We're canceling out 1 mole of NO2 on the left reactant side with 1 mole of NO2 on the product side. Woo. Then we go to NO3. NO3 is present on the reaction side, and it's present on the product side. This is a special type of molecule that we are calling the intermediate. So this is what an intermediate is. It's produced in one reaction and used up in the next. It gets cancels out. It is not included. Ooh, I think I damaged my pen a little. No. All right, well, it might be really thin, but hopefully you can still see it. So NO3 present, generated in the first reaction, used up in the second. This is an intermediate. Oh, that's tragic. It's not working. So NO3 is an intermediate. It is not included in this reaction equation. I'll try again. I'm going to type it out. All right, NO3 is an intermediate. It does not appear in the overall equation because it is consumed after it is produced. Questions up there? Great. So NO3, let me make that larger. NO3 is an intermediate. Again, we do not put it in the overall equation. So we're done with NO3. Yep, now let's go to the next reagent, which was carbon monoxide. Carbon monoxide is present as a reagent. It is not present as a product at all. So this remains a reagent in the overall reaction. And then we're done with reagents. Next, we look at products. We have NO on the right side, not on the left at all. So NO remains a product. Carbon dioxide also remains a product. So we've got two products over here. So using the elementary steps, adding them together, we get this overall equation. If you were to write the equation, or you were to look up the reaction of NO2 reacting with carbon monoxide, this is what you see. But really it occurs through these individual steps. And these two steps can be used to describe the rate of the overall reaction. So these elementary steps are useful. I'm not done. We're going to the next slide. Yeah. It's not because it's used and needed for the reaction to occur. It's a reagent. Like for the first step to occur, you need NO2. Yeah.
Is it always going to be written? Is it always going to be written like NO2 plus NO2, or would it be a 2 coefficient?
It could have a 2 coefficient. Okay. Yeah, that's possible too. Okay, so we can use rate information from the elementary steps to describe the overall rate. That's what we describe as molecularity. So the number of molecules involved in an elementary step determines its molecularity. We can go right from an elementary step and write the rate law without having to calculate reaction order. As long as you're working with an elementary step, you know it is an elementary step, then you can look at this and determine the rate law. For this first reaction, we have AB, so that is one reagent forming two products. But the key here is that we have one reagent molecule. That tells us this is a unimolecular reaction. And the rate is equal to rate constant times the concentration of AB. with the exponent 1 because it's unimolecular. So remember last week we had to get information from multiple experiments, determine reaction order that way. If you have an elementary reaction, you can determine the rate law just by the molecularity. Yeah. This one, for example, in contrast, the rate would be K times the concentration of A squared because there's a 2 coefficient there. We'll fill in the rest of the table on Friday though. Have a good Monday.
I have a question.
Yeah.